Welcome to the nature of acids and bases. So here we have a little bit of an introduction to acid-base chemistry and the sorts of things that we consider acids and bases. So acids and bases are two classes of substances with certain properties. Acids generally taste sour, so think of things like citrus fruits, lemons, limes, oranges. Acids feel somewhat sticky, at least compared to water. They react with many metals to form hydrogen gas. Acids have a pH less than 7, and acids are also electrolytes. Bases, on the other hand, instead of tasting sour, they taste bitter. They feel slippery. That is, if you compare a base, if you get a base on your hand and water on the other hand, the hand with the base is going to feel slipperier. It's going to feel almost as if you have some oil in it. The bases also react with oils and greases. In other words, these things make good cleaners, so we use them for soaps and things like drain cleaner because they tend to react with the things that we want to clean up. Bases have a pH that is greater than 7, and bases are also electrolytes. So, some examples of acids are citric acid. Again, this is the acid that is in lemons, limes, oranges that makes them taste sour, because again, acids taste sour. Ascorbic acid, vitamin C. There's also a good bit of vitamin C in these citrus fruits, but the citric acid is at a higher concentration. Acetic acid, which is vinegar. So if you've tasted vinegar, you also know that this is sort of a sour taste. Carbonic acid, this is the carbonation that's in soda. So this is, again, what makes the soda taste somewhat sour to us. Now, you may be thinking, well, soda doesn't taste that sour to me. That's because there's a lot of sugar in, or a sugar substitute in sodas that generally masks that sour taste. Lactic acid is in milk. Gastric acid, the stomach acid in your stomach is at a concentration of about 0.1 molar, and that's hydrochloric acid. So this is why after you've thrown up, if you don't have much left in your stomach, but you've got this acid, you get a really sour taste in your mouth. That's this gastric acid. That's that hydrochloric acid mixed with some other things like bile and things like that. And that tastes very, very bad because it's an acid. So some examples of bases are soaps or detergents. Sodium hydroxide, this is lye. Ammonia. Note that there's a difference between ammonia and ammonium with an M. So ammonia is NH3. Ammonium is NH4+. So the ammonia is a neutral species. It's a neutral compound that's got 1 nitrogen atom and 3 hydrogen atoms covalently bonded together. The ammonium is an ion because it's got a +1 charge, and it has 4 hydrogens and 1 nitrogen. It's basically the ammonia plus 1 H+ ion, and we'll look into that again a little bit later in the video. Another example of a base is sodium bicarbonate, which is the baking soda that you may be putting in cookies and things like that, that cause them to rise and get fluffy. So let's look at one definition of an acid and a base. We're going to look at the Arrhenius definition. So in the Arrhenius definition of acids and bases, an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. So this H+ is a hydrogen ion. So if we take something like the gastric acid, the hydrochloric acid that's in your stomach, and we dissolve that in water, so we've got this double-headed arrow, meaning we can go either way, and over it we've put this H2O, meaning that the water there is not reacting with the hydrochloric acid. If it were reacting, then the water would be on this side. It would be a reactant. If it were a product, so if we were forming it, it would be on the right side, but over the arrow means that we have it around, we need that water in order to have this reaction take place, but it's not actually reacting itself. It's just around it. So we have the hydrochloric acid, and it's splitting up into 2 ions, the H+ ion and the Cl-. So we have the hydrogen ion and the chloride ion. And so if our hydrochloric acid dissociates, we call this process dissociation because these two ions, the cation here and the anion, are dissociating from one another. They are no longer associated. They can move around independently in solution. So this dissociation process of our acid forms H plus ions, which means the concentration of our hydrogen ions is going to go up. So on the other hand, a base is a substance that, when dissolved in water, increases the concentration of hydroxide ions, these OH minus ions. So if we take something like sodium hydroxide and we dissolve it, again, putting it in water, we get sodium ions and hydroxide ions. So if we're adding hydroxide ions to the solution, then we're increasing the concentration of hydroxide ions. So sodium hydroxide is a base. So note here that the Arrhenius definition is limiting us to aqueous solutions. We have to be putting our acid or our base into water. If we're working with some other solvent, or if these are pure liquids, let's say, the Arrhenius definition doesn't talk about them. It's not saying they are or are not acids or bases, but the Arrhenius definition doesn't say anything. It doesn't apply in those cases. So the Arrhenius definition is a little bit limiting here, but we're going to work with it for now, and we'll go on to another definition later on. So let's look at what happens when we have the hydrogen ion in water. If we put our hydrogen ion, our hydrogen ion is acting as just a proton, because when hydrogen starts out, if we have a neutral hydrogen atom, we have one proton in the nucleus and one electron orbiting the nucleus. This is assuming that we have hydrogen 1. If we have deuterium, then we have a neutron in there as well. But most of the hydrogen atoms around have an atomic mass of 1, and so there's just a single proton in the nucleus, and then we've got an electron out in the electron cloud somewhere. But if we give that a +1 charge, that means we've taken that electron and we've ripped it off the atom. And now the only thing we have left is just the nucleus of the atom. There are no more electrons left, which means the only thing we have is just a single proton. So we often call hydrogen ion a proton, and this is, again, because it's just a proton with no surrounding valence electrons. There are no core electrons in this case either. And if we put this proton, this hydrogen ion, into water, it will form clusters with water. So basically we have the hydrogen ion, it will react with a neutral water molecule, and it will form this H3O plus ion, and this is what we call hydronium ion here. It also forms additional clusters. We can get larger clusters forming with 2 water molecules involved, H5O2 plus, or 3 water molecules, H7O3 plus, or 4 water molecules, H9O4 plus, and so on. The point here is that the hydrogen ion doesn't really exist in water as a single proton moving around. It really is complexed with some number of other water molecules. The simplest of them is this hydronium ion. Now, in chemistry, we generally discuss the proton, hydrogen ion, and the hydronium ion as the same sort of thing, because they're related, and so we generally, if we're referring to either one of these concentrations, and we're not talking about these other concentrations, if we're just referred to one of these two, then we're using the terms interchangeably, usually. So to keep things simpler, we usually leave out the hydronium and we just discuss things in terms of the hydrogen ion, even though the hydronium ion is far more concentrated than the hydrogen ion is in water. All right, so if we have pure water and nothing else around, we still have some hydrogen ions in solution, and we have some hydroxide ions in solution. And this is because water undergoes what we call autoionization. Auto meaning it does this all by itself, and it ionizes. So if we have 2 water molecules, they will split apart. One of them forms a hydronium. Basically, one of the water molecules is stealing a proton from the other one, and then we have the remainder of our second water molecule, the one that lost the proton, and that's the hydroxide ion. So we can either write that this way as 2 two water molecules, one of which is stealing a proton from the other one, and then we're forming a hydronium ion here and hydroxide ion here. Or we can write that this way, where we have one water molecule that's splitting apart into hydrogen ion and hydroxide ion. These two equations say essentially the same thing. It's just two different ways of looking at it, whether we're calling the hydrogen ion an H plus or a hydronium ion H3O plus in solution. So what this means is that the water will always contain some amount of hydrogen ions and some amount of hydroxide ions, because this process happens regardless of what other solutes you have dissolved. Now we can change how the relative concentrations of hydrogen ions and hydroxide ions by adding in an acid or a base, but this process will still happen even if we have an acid or a base in solution. And this means that it limits what can happen in water. So, because water then can form hydrogen ions, it can act like an acid, according to the Arrhenius definition. But because it can form hydroxide ions, it's also acting like a base. And we call these sorts of substances that can act as either acids or bases, we call these amphiprotic or amphoteric. So this is similar to amphibian, which can go both in the water and on land. Amphiprotic means we can do both sorts of behaviors with respect to protons. That's the protic part. So they can either produce the protons, or they can react with them in the way that hydroxide would. So we've talked about the Arrhenius definition of acids and bases, and now let's look at another definition, the Brønsted-Lowry definition. So let's focus here on the protons. So the Brønsted-Lowry definitions of acids and bases say that an acid is a species that donates a proton, and a base is a species that accepts a proton. So basically what's going on here is when you have an acid and a base react, the acid is the one that's giving up the proton, and the base is the one that's accepting the proton. It's reacting with that proton to form something else. Or another way to look at this is the base is stealing a proton from the acid. And that proton, that H plus, is moving from the acid to the base. So, note here that anything classified as an Arrhenius acid or an Arrhenius base will also be classified as a Brønsted-Lowry acid or a Brønsted-Lowry base. Because anything that produces H plus in water will donate a proton. Anything that produces hydroxide ions in water, that hydroxide ion will accept a proton. So that base, that Arrhenius base will act as a Brønsted-Lowry base as well, because it will accept a proton from an acid. So what this means is that now our Brønsted-Lowry definition is a little bit wider. We no longer have to talk about acids and bases in water. We don't have to have aqueous solutions. So now we can move on and talk about other solvents involved here as well. So let's look at an example here. Here we have ammonia, not an ammonium, ammonia, NH3, reacting with water, and that forms ammonium, the NH4+, and a hydroxide ion. So, which one is acting as the acid and which one is acting as the base? Well, ammonia, the NH3, is taking a proton from the water to form ammonium. Right? From here to there, we've added an H+, which means the ammonia is acting as the base, the Brønsted-Lowry base. Note here that this reaction, this equation, may appear to show that ammonia is producing hydroxide. Right? That we have the ammonia and that's producing hydroxide ion, but it's actually the water here that is producing the hydroxide ion. Because really, we have the water splitting apart, this autoionization process to form a proton, and the hydroxide. This is where the hydroxide is coming from, there. And then that proton goes on and reacts with our ammonia to form ammonium. So this means that ammonia is not an Arrhenius base, but it is classified as a Bronsted-Lowry base. So again, our Bronsted-Lowry definition is a little bit wider. It encompasses more compounds. And this is better because it gives us a better description of the reactivity of various compounds. So again, here we've got our two split up reactions, and note here that the proton is being donated by our water molecule. Right? This proton here came from the water molecule, which means that the water molecule is acting as the Bronsted-Lowry acid. So again, we've seen that water can act as an acid. So let's look at the formation of ammonium from ammonia one more time. So we have our NH3 and we add H+, and that gives us NH4+. But because this is an equilibrium reaction, we can write this reaction reversed. We can write the ammonium on the left side, and if that splits apart, if that dissociates, it will dissociate into ammonia and a proton, a hydrogen ion. So this reaction is just the reverse of that one. But note that now, in this reaction, we have ammonium splitting apart to form ammonia and a proton, which means the ammonium can donate a proton. Well, something that donates a proton is an acid. So here we have a base, ammonia, accepting a proton to become ammonium, but ammonium is an acid. So we have a base reacting with a proton that gives us an acid. So the ammonia again is acting like a base, the ammonium, NH4+, is acting like an acid, and this is a pair of species that we call a conjugate acid-base pair. So the conjugate acid is the species formed by adding a proton to a base. That's our ammonium here. If we have our ammonia and we add a proton, we get ammonium. We have our base, and we form our conjugate acid when we add a proton to it. On the other hand, a conjugate base is that part of an acid that remains after the acid donates a proton. So if we have our acid, ammonium, and it donates a proton to something else, to some base, then the conjugate base that we have here is ammonia. After we remove a proton from ammonium, we're left with ammonia. So ammonia is the conjugate base to ammonium, and ammonium is the conjugate acid to ammonia. So every acid has a conjugate base, every base has a conjugate acid, and so these are called a conjugate acid-base pair. Again, ammonia is a base, ammonium is its conjugate acid, ammonium is an acid, ammonia is its conjugate base. So every acid here has a conjugate base, and every base has a conjugate acid. And that was the nature of acids and bases.